Hi everyone, my name is Jinlong Feng from City College of New York. Today I'm here presenting our work about subsurface pipes detection using DNN-based backprojection on GPR data. First, let's review the GPR and talk about the problems we want to solve in this work. Ground penetration radar emits a scan from its antenna. As depicted in the middle image, when the GPR moves on the ground over an object along trajectory, it produces a series of A-scans at different positions, and this ensemble of A-scans forms a B-scan. The leftmost figure shows the backprojection image, which is a process of aggregation that would convert the different amplitude energy into the semisphere format at different depths, which follows the equation at the bottom of the slide. As illustrated in this figure, the brighter semisphere indicates the higher amplitude part in A-scan. And in the meanwhile, the radius of each semisphere in the backprojection image indicates the depth of the A-scan pulse. However, towards the inspection of subsurface targets, there are still some challenges needed to be solved as following. Firstly, the hyperbolic feature in GPR B-scan is too abstract to identify by normal users, so that it heavily relies on the expert's efforts. Secondly, the methods that interpret GPR B-scan image are either theoretical, complicated, or computational costly. To address the above challenges, we take advantage of GPR Max to build a synthetic testing environment which simulates a real non-destructive testing condition, since it's very hard to get the ground truth of the underground objects from the real environment in non-destructive testing. We built 12 different synthetic concrete slabs with different size and design in total, and once we get the synthetic B-scan image, we firstly use UNet model to filter the noise out from the raw B-scan data, and then stack them into an aggregated 3D backprojected format by using the sliding window crop operation. Then we proposed a DNN-based migration model, MigrationNet, to interpret the aggregated backprojected data. As you can see, the input data is 3D data that has 256 channels, and further downsampling into 128 and 64 channels in spatial domain. Our encoder is a multiple spatial resolution encoder, which has different kernel size in the first max pole layer, so that it allows the final output feature map has the same size according to the different resolution of the input. The decoder consists of 5 upsampling groups, where each group contains 2 convolutional layers and 1 deconvolutional layer. Note that this plus sign presents escape connection coming from the encoder layer. Our last design is inspired by the following works. We combined the L1, which demonstrates the structure compression loss, and the L2 across intraphase loss together. Experiments show that the joint loss has a better prediction performance than only using cross intraphase loss, since the structure compression loss contributes to our task and makes the prediction image be more like the real cross-section image of the object model. Now let's discuss experiment results. Figure 1 shows the migration results between the conventional method and our DNN-based method, which shows our predicted image has a better performance than the traditional migration image. And table 1 shows how inertial parameter affects to our model training process. Another interesting topic is that how does the channel of the stacked backprojection data affect the migration performance. Thus, we conduct this experiment to verify the encoder performance with different input resolution. As shown in the table 2, the current combination of our multi-resolution encoder has the best performance compared to other tests, which indicates the local geometrical and thematic feature of backproject data could be better extracted through our encoder. At last, we also compared the noise robustness between our method and conventional method, since DNN model is good against random noise. As we can see in the figure 2 and table 3, the experiment shows that our method gets much less effects against the noise input we set up.